Good afternoon, everyone. So welcome to my YouTube channel, Maths Avatarm. So hope you are all good and you are doing well. So today we are going to see this question. Okay. Let Fn I to R be sequence of function converging uniformly to F on I. I is interval. Okay. And we have taken a fixed point x naught from interval I, and it satisfies this point have property that limit extending to x naught Fn x is equal to an for each n. Then the following statements hold. An becomes a convergent sequence and limit extending to x naught fx is equal to limit n tending to infinity an. It means limit of sequence is limit extending to x naught of fx and limit of sequence both are same. Okay. So let's prove it. Okay. So we are going to see its solution. Fn, first part we are saying Fn converging to F uniformly on I. So given if Fn converging to F uniformly, what does it mean? It means F, this sequence is uniformly Cauchy. So this implies Fn B, Fn is the Cauchy sequence. Is uniformly Cauchy. Okay. Cauchy on I. So let epsilon greater than 0 is given. Then since Fn is uniformly Cauchy, there exists capital N belongs to N such that F n plus p x minus f n x is less than epsilon by 2 for all n greater than equal to capital N, p greater than equal to 1, and x belongs to I for all x belongs to I. Okay. Okay. Now keep n plus p and n fixed. Let's say it in 1 and letting x tending to x naught in 1. We get what we get when we take limit x tending to x naught. What will be this? This will be a n plus p minus a n less than equal to epsilon by 2 for all and for all n greater than equal to capital N and p greater than equal to 1. Okay. But this is strictly less than epsilon. So what it means? A n plus p minus a n is less than epsilon for all n greater than equal to n and p greater than equal to 1. So what does it mean? It means this an is Cauchy sequence in R, and we know that Cauchy sequence is always convergent in R because R is complete. Okay. Okay. It means an is a Cauchy sequence, and Cauchy sequence is always convergent since R is complete and an is Cauchy sequence in R, we get an is convergent. Okay, an is convergent in R. Okay, so an is convergent. Okay, now we are going to prove second statement, that limit is equal to this. Okay, so one is done. So an, this sequence an is convergent. Okay, let's say an converges to a in R. Its limit is a. Okay, we are assuming that it's limiting a, denoting by a. Okay, Fn converging to F uniformly. Okay, let epsilon greater than 0. There exists n1 belongs to n such that Fn x minus fx is less than epsilon by 3 for all n greater than capital N1 and x belongs to I. Okay, let's say it equation number 1. Equation number 2, sorry. Okay, equation number 2. Now an converges to a. What does it mean? There exists capital N2 belongs to n such that an minus a is less than epsilon by 3 for all n greater than equal to capital N. Let's say it equation number 3. Next, limit x tends to x naught is Fn. Sorry, 1 minute. Take n is equal to maximum of n1 and n2. Next, limit x tends to x naught Fn. This is an. It is given in question. Okay, it is given in assumption. Then what is the meaning of this? What is the meaning? It means that there exists delta greater than 0 such that Fn x minus an less than epsilon by 3 for all x belongs to I such that x minus x naught less than delta. Okay, let's say it's equation number 4. Okay, this is equation number 4. So we have three equations, equation number 2, 3 and 4. Okay, now let x belongs to I such that 0 x minus x naught less than delta. We have what we have f n. Okay, x minus A is equal to f n x minus f n x plus f n x minus a n x plus a n x minus a. What is this? F n x minus f n x plus f n x minus a n. Sorry, a n. Only a n is not a n x. It is a n. So it is a n minus a. Okay. So use triangle infinity a here plus a n minus a. Okay. So what about this? This is less than epsilon by 3 by equation number 2. Okay. Okay. Sorry, 1 minute. So Fn minus Fx minus. Sorry, 1 minute. I have made some mistake here. I should write F here. Okay, because we want to show that limit x tending to f is equal to a. So we have to take here fx. So now you add and subtract fnx and add and subtract an. So we have what? So by equation number 2, what we have? We have this one. Okay, because fnx minus fx is less than epsilon for all x belongs to I and greater than equal to capital N. So we have taken n is equal to n. So it is less than epsilon by 3. So we got epsilon by 3. And what about this? This is also epsilon by 3 by equation number 3. And what about this? By equation number, this is equation number 4. By equation number 4, we have epsilon by 3. And this is by equation number 3, epsilon by 3. Okay. So what we have? We have, this is equal to epsilon. So what we have? We have fx, we get there exists delta greater than 0 such that fx minus a is less than epsilon for all x belongs to I with, okay. So what does it mean? It means limit x tend to x naught fx is a. But what is a? A is limit of, this is limit of. So we are done. So okay, second part is also done. So what is the conclusion? So it means in other language, so we have limit naught, we have this limit fx is equal to limit n tending to infinity an. You put the value of fx. What is fx? Limit x tending to x naught. What is fx? This is limit of n tending to infinity f and x. Fx is nothing but this because fn converging to f uniform. And what is this? This is limit extending to x naught f and x. Okay. It means, what is the meaning of this? It means we can change the limit. In this we are changing the limit. We can interchange the limit. Answer will be same. So this is the conclusion. Okay. Now we are going to see another question. Question number 2. That was question number 1. Let this series n goes to 1 to infinity f and x. Okay. Converges uniformly okay uh, uniformly to converges uniformly to converges uniformly on I some interval such that limit extending to x naught f and x is an for some x naught belongs to I. Then number 1, summation this sequence k goes to 1 to n f a k converges. Okay. Second one limit extending to x naught summation n goes to 1 to infinity f and x okay is nothing but limit n tending to infinity okay an. So we have to prove this. Okay. Proof. Okay. This n goes to 1 to infinity an fn f and x converges uniformly to converges uniformly on I. Uniformly on I. Okay. And it is given such that limit x tends to x naught f and x is an. Okay. For all n belongs to n. Okay. Now you see that I am taking my I am taking my capital F n is equal to summation k goes to 1 to n. I am taking this F n x. Okay. Then what does it mean? It means F n, this sequence converges uniformly on I. Okay. Converges uniformly on I to some function. We are not writing that function. And what about this? Limit n tending to, x tending to x naught. X tending to x naught. F n x. Limit x tending to x naught. Summation k goes to 1 to n. F n x. What is this? Because this is a finite number. Limit will be distributed in sum. F k x. So k will be k. Okay. So what is this? This is nothing but summation k goes to 1 to n a k. Okay. So by question number 1, what we have? Let's say it capital A, capital A n. Capital A n for each n belongs to n. Okay. By question number 1, what we have? By problem 1 or question 1, we can say question 1. We have that an converges. It means this summation k goes to 1 to n a k converges. Okay. So 1 is done. So one part is done. Okay. Converges. Second part, again by question number, again by question 1, we have what we have? That limit x tends to x naught. The limit of function is limit n tending to infinity f1 x by naught. We have written in naught. Question number 1, but we have mentioned it in naught. When we write a naught, okay, it is nothing but limit n tending to an. Okay. Because let's say it capital Fx. So this is capital Fx. Okay. So this is limit x tending to infinity. What is this? This is k goes to 1 to infinity f k x. This is what limit k goes to 1 to infinity kt. Or simply we can write it means limit x tends to x naught summation n goes to 1 to infinity f and x is equal to n goes to 1 to infinity an. Okay, so second part is also done. What was second part? Second part was this. Okay, so we have done this. Okay, so thank you very much for today's session. If you have any problem related to this session, you can comment me on my YouTube channel. I will see it in next session. So thank you very much for today's session. Kindly like, share, comment, and subscribe my YouTube channel. Thank you very much. Thank you very much for today's lecture.